You can find most of our past presentations, but now by typing in tinyurl.com/C like creation, F like fellowship, and Santee, Santee. We have links there to our 3 channels on BitChute, Rumble, and YouTube, where you can find most of our past presentations. You can also email us at Creation Fellowship Santee to get on our email list so you don't miss any upcoming speakers, and we never spam. Joe and Stacy Gaona have been our friends and members for many years, and since Joe's homegoing last year, we always want to honor his memory by mentioning the continuing work of his ministry throughout all ages. Throughout All Ages Ministries focuses on reaching people with the gospel, contending for the faith, and stirring the body to love and good works. Although they enjoy street witnessing and other evangelistic events, God has blessed them with the opportunity to go into public schools and speak on relevant topics to young people. You can learn more about Throughout All Ages Ministries at throughoutallages.com. And once again, we just want to thank Spike Psarris, who's with us tonight. I'll introduce him too, but just as a reminder, we have some great upcoming presentations for the next 6 weeks. Next week, we'll be hosting Dr. Jason Lyle, who will be talking about quantum physics. After that, we have Nate Loper, who will be here with us for the Grand Canyon, talk about the Grand Canyon. We have Mike Gendron coming to talk to us about how to reach Catholics for Christ. Oh, and then my slideshow ended, but you can find more of our upcoming speakers by visiting our Facebook page, which is Creation Fellowship Santee. So now for tonight, Spike Psarris is an electrical engineer with experience working in the United States military space program. It was during that time that he came to the realization that scientific evidence supports the creation model, not evolution. That realization turned him from an atheist to a Christian. Praise the Lord. Now Spike is a Logos Research Ambassador and speaks at churches, camps, conferences, and homeschool and other events. We're excited to have him speak for us tonight on the topic of thermodynamics confirms creation. And if you have questions and you're following along on Zoom or on Facebook, please feel free to put your questions into the chat. And at the end, I will ask him some of those questions during our live Q&A. With that, I'm happy to turn it over to you, Spike.
Well, thank you very much. And thank you everyone for having me. Haven't used Zoom in a while, so if there's some kind of glitch there, hopefully that will go well. Let's start by seeing if the share screen button works. Let's see.
Are we going in outer space, or is that just a background?
Well, the air would be a little rarefied were that the case. Okay, so share screen is going to take a second to get going, unfortunately. Sorry for the delay. Some of these things. Uh-oh, I have to quit Zoom and come back in order for my share screen to work.
Why? Maybe I can help.
No, it's a security issue. Oh, I will be right back. Excuse me.
Okay, we will be looking for you to come back.
Okay.
Once again, this is Creation Fellowship Santee, and we're here tonight with Spike Psarris on thermodynamics confirms creation.
PowerPoint back up so they can see our upcoming presentation.
Yeah, I might have already closed the PowerPoint.
Okay.
But in coming weeks, we have some great speakers. We have Dr. Jason Lyle next week. We have the week after Nate Loper talking about the Grand Canyon and several other great presentations in November. In November, we'll be doing animal eyes, how they're the amazing animal eyes with Bill Morgan. We also have Brian Lauer coming to talk to us about the World Economic Forum. And we'll be ending our season this year on November 17th with Pastor Tom Lee, who will be talking about repentance. So those are some things to be looking forward to. All right, Spike, we see you're back.
I'm back. I apologize for that. I joined the meeting early, hoping that
Yeah.
Well, we
to do things ahead of time, and it still didn't quite work. Okay.
No worries.
Am I sharing my screen?
Yes, we can see it.
Okay. And is this the whole screen being occupied now? Hopefully.
It's perfect.
All right, great. Well, after the I mentioned a Zoom glitch, and we have one right at the gate. but we're back. I'm back. Thanks everyone for having me. My privilege to be here with you all this evening. And we're going to talk about what I hope will be a fun topic, thermodynamics. As creation talks go, this one maybe will be a little unusual. Most creation talks tend to focus on, I hate to use the word basic, but there's a lot of common themes. There's dinosaurs, radiometric dating, age of the Earth. There's a lot of questions that are especially important and that get covered quite frequently in creation discussions. But if you've been around the movement for a while, you might, and as much as I still love dinosaur talks, sometimes we want to hear something a little different. And that will be one of our efforts here this evening. It's kind of an unusual, narrow sort of focus, but at the same time, I think it's important. And I'm going to argue here something that I've never really heard spoken about. The Bible says that the heavens declare the glory of God. So we know from that astronomy is a means through which we can perceive more of God's glory. But what about the other sciences? I mean, the Bible doesn't say specifically about many of the other areas of investigation into the creation around us. But should it also be the same that we should be able to perceive God's glory through biology, for example? And indeed, I argue that we can. I mean, looking at microbiology, there's molecular machines and there's engineering principles that we can see at work. Even within DNA, there's computer science and cryptography principles at work. By studying these things, we can perceive more of God's glory that way. In ornithology, I mean, birds are amazing. We could talk for hours about some of the amazing aspects of birds and all the even iridescence and feathers. The hummingbird that I'm showing here and the way that it flies is all these, to me, amazing things that we can perceive about God's abilities that way and his glory perceptible to us there. Paleontology shows us some of the amazing diversity of creatures that have existed through history. And even as amazing as the animals that we see in the world today, there's this even stranger and more wonderful ones in the past. Again, we can see more of God's abilities, his creativity, his power there. Geology is the study of the earth, and through that we can perceive more of God's interaction with mankind. I mean, much of geological formations is a result of a global flood. So I'm arguing here that all of these sciences give us different aspects or different, the ability to see different aspects of God's glory as creator and sovereign of the universe. But what about physics? How do we perceive God's glory in physics? I mean, is physics, we tend to think of it as more of a utilitarian and just a very practical thing. But no, I'm going to argue that every aspect of science, including physics and including even a narrow area within physics, such as thermodynamics, can help us perceive more of God's glory. So that's my overall theme here this evening. Now, some of us may be familiar with thermodynamics, others maybe not so much. This will be a hopefully non-technical presentation and still accessible in what we'll be talking about, but hopefully still interesting to everyone. So let's start by talking about what thermodynamics is. Thermodynamics is a combination of two root words here. Thermo means heat, and dynamics means change or motion. So the word literally means the change of heat through time. And there are several laws of thermodynamics. I'll be focusing on two specifically. The first law of thermodynamics, I know some people are familiar with this, but some people may not be. So we'll mention them up front and then talk about them in more depth here in a few minutes. The first law of thermodynamics says that matter and energy cannot be created or destroyed. And we'll see here shortly why this is important to us. The second law of thermodynamics says, and I'm abbreviated as 2LOT in some of my slides here, says that entropy in a closed system will always increase. And I know many of us have heard of these laws, but may not be familiar with all the aspects of them and exactly how they apply to creation. In fact, some people talk about these laws and do try to apply them to biblical history. For example, there's sometimes discussion in creation circles about whether or not the second law of thermodynamics, that entropy will always increase, is the result of the fall of man, recorded in the book of Genesis. That when Adam sinned and the creation was subsequently cursed, perhaps that is when the Lord instituted the second law of thermodynamics. And we'll talk here about that shortly in more detail. Overall, though, there's many misconceptions about the laws of thermodynamics. Both sides have applied them in the origins debate, being evolutionist and creationist. And both sides, unfortunately, make a lot of mistakes in doing so. There's a lot of incorrect arguments out there. So one of our purposes tonight is to correct the misconceptions and at the same time say, well, how can we use these laws of physics correctly? When we understand thermodynamics correctly, it actually opens up some interesting areas of insight for us. First of all, thermodynamics can be used to show that our solar system is actually young and not billions of years old. It shows that life requires an intelligent designer. It shows that any non-creationary, any secular model of origins is self-refuting. It disproves itself. And we'll talk more about that here shortly. And it also confirms overall that a supernatural creator is indeed responsible for the universe's existence. So here's an outline of what we'll be talking about here this evening. We'll start by listing a few misconceptions, a few ways that the laws of thermodynamics are used incorrectly in the origins debate. Then we'll talk about how the first and second laws work. Some people will be familiar with this, but I know some people won't be. So we'll cover that. And this has been known since the 1800s. Then once we're equipped with a little more information about what the laws are and how they work, then we'll talk about their implications for origins. And we'll clear up some misconceptions after that. Having established how the laws work and some ways that they shouldn't be misused, we will then talk about why the laws of thermodynamics work. And moving forward in time a bit, this wasn't even understood until the late 1800s, early 1900s. So thermodynamics was known for a while to work, but it wasn't known at first why they worked. And understanding why they work has additional implications for origins that we will be discussing. So here's an overview of our overall time here this evening, and we'll start with the first one. Misconceptions. So a lot of people have heard that the second law of thermodynamics says that entropy in a closed system will always increase. But here's a question: what is entropy? Well, a lot of people, when you ask that question, will say, well, entropy represents disorder, disorganization. And indeed, we can find lots of examples in the world around us, maybe some very close to home, of disorder and disorganization. But is this really what entropy is? Is the young man in this cartoon here correct when he blames entropy for the condition of the room that he's in? Well, no, actually. Disorder and disorganization is a very subjective thing. It's not a quantifiable value. I mean, how much disorder is there in this garage that I'm showing you a picture of? There's no way to measure that. And if we're going to talk about physics, we need to have measurable, quantifiable values to work with, right? So disorder and disorganization is a concept that's perhaps useful to us in our lives in certain ways, but it's not the same as entropy. And this is actually the source of a lot of misunderstandings and incorrect arguments in the origins debate. For example, Henry Morris and John Whitcomb, who were giants of the creation movement, I mean, did amazing things. Unfortunately, we're not correct in everything they said. And here's a quote where they're getting into some of the things we've already talked about. They said creation, or biologists imply by evolution, actually has been accomplished by means of creative processes, which are now replaced by the deteriorative processes implicit in the second law. The latter are probably a part of the curse placed upon the earth as a result of the entrance of sin in Genesis 3, the bondage of decay to which it has been subjected by God for the present age. So they're arguing that the second law is actually the result of the curse and its deterioration over time. Another thing you will see is sometimes Christians will say evolution isn't possible because it's a decrease in entropy, because things are getting more and more organized, if you will, over time as they evolve, according to evolutionary claims. And because that means entropy would be going down instead of up, that means it's impossible. This, too, is a bad argument because this is a misunderstanding of what entropy actually is. And now, don't get me wrong, I'm not saying evolution is possible. Molecules to man evolution didn't happen and can't happen. But that doesn't mean that we should be using bad arguments to show this. There's good arguments we should be using, and so we shouldn't be using incorrect ones. Dr. Duane Gish, another giant in the history of the creation movement, talked about entropy being associated with order and complexity. He said, this fundamental law of science talking about the second law of thermodynamics, tells us that an isolated or closed system will never increase in order and complexity. It will never become more highly organized. Now, this is an explicit association with entropy and order and complexity. And this is unfortunate because, as I've already said, this is an incorrect argument. And people have actually used that as an argument against creation. There was a debate in which Dr. Gish used this, and apparently his opponent at the time triumphantly held up a bottle of salad dressing that he had brought with him, shook it up to show the oil and the vinegar in the salad dressing mix, and then showed it to everyone, and voila, right in front of everybody's eyes, the oil and vinegar separated. And he said, well, look, here's a spontaneous increase in the order and complexity, thus disproving Dr. Gish's argument that he just made. Now, the opponent in this debate was not actually disproving the second law. He was actually disproving an incorrect argument that Dr. Gish had just made. So again, supporting the idea that we need to be careful that the arguments we make are correct. Otherwise, our opponents will use that against us. Creationists, however, are not the only ones who have incorrectly used these laws in their arguments. The evolutionary side of the debate has also used them incorrectly. For example, you will sometimes hear crystal formation being offered as evidence that order and complexity can spontaneously increase in natural systems. I've even seen an evolutionist make an argument that a baby growing is an argument against the second law, or at least creationist applications of the second law. This author said, can a few cells floating around in a warm liquid turn into something complex? Clearly, material can acquire complex form. Any claim that some law forbids it is a false claim. Now, we're going to come back to some of these arguments here later. My point mentioning them now is just kind of set the stage as to why this is an important issue to talk about. It's more than just an interesting thing to talk about in an online Zoom meeting for a while. This actually has implications and discussions with people, and I argue that it's important for us to understand these laws correctly, because there's along with not using them incorrectly, there's a lot of really good uses of these laws from our perspective. But before we can cover that, let's talk about how the first and second laws work. And we're going to talk about a little history along the way and ask the question, well, what is thermodynamics anyway? And interesting, my slide's not working. There we go. Some weird Zoom build. What is thermodynamics anyway? Where did these laws come from? It actually comes from coal mining in England, of all things. Kind of an obscure little fact of history here. England was blessed with large coal deposits. These are primarily the result of the Genesis flood, but for whatever reason, the island that England is on wound up with a higher than common number of deposits with rich coal seams in them. And in the 1800s, the nation had started to exploit these quite a bit. There was an engine called the Newcomen engine, an early version of the steam engine. It was very inefficient. It has an efficiency, as known today, of only about 0.5%. So almost all of the energy of the coal that was burned in it was wasted. But England had so much coal to burn that they were able to produce a lot of energy from this. And this is basically the foundation of what we now know as the Industrial Revolution, where in just a generation or two, the country went from a primarily rural agrarian society to an industrial behemoth in the world at the time. And England's, I should say Britain's economy really boomed as a result of all this cheap, abundant energy that they had available to them. Specifically in the area of textiles. A lot of this early energy production was devoted to powering textile production. And the other countries in Europe noticed that Britain's economy was booming while theirs was suffering in comparison. So scientists on continental Europe became intensely interested in how the British were doing this and how they could do it as well. So they had commercial motivation in doing this. And they started asking questions like, well, let's look at steam engines. Why do they work? And how can they be made to work more efficiently? The European scientists were more interested in this than the British scientists were. And of course, I understand Britain's part of England. You understand, continental Europeans, I should say. Scientists, they were more interested in making more efficient engines than the British were because they didn't have such abundant, cheap coal reserves as Britain did. So because their coal is more expensive and less abundant, they needed to get more energy out of every pound, every kilogram of coal that they put in their engines. So this was really the reason why people started to study steam engines and figure out how to make them work better. And that raised the question of, well, these things run off of heat. What is heat? There was actually some misunderstanding about this for a while. Heat was, for example, for a while thought to be a fluid. Today we have an understanding of what's called the kinetic theory of heat, where heat actually represents the vibration of the atoms in a material. So the hotter the material is, the more intensely the molecules within it are vibrating. And that's important because it allows us to understand how heat transfers from one material to the other. A transfer of thermal energy, i.e. heat, requires a difference in temperature, it turns out, because you have the different molecules vibrating, and if one is vibrating more intensely than the other, when they come in thermal contact, as it's called, in other words, heat transfer is possible, the vibration will basically equalize. The one that's vibrating more will stimulate the one who's vibrating less to vibrate more until they are both vibrating with an equal intensity. And I'm trying to simplify my wording here a little bit, not to get too technical. But that's the basic concept here, is that heat is the result of the vibration of molecules within a material. And that vibrational energy, if you will, can transfer among molecules, and that's how heat itself transfers. But that requires a difference in temperature to do that. One molecule has to be vibrating more intensely than the other in order for the vibration to transfer. And this has some implications. For example, it means, among other things, that small bodies cool off faster than large bodies. So imagine these two metal balls here are at the same temperature. They contain, same temperature, but they're in an environment that's cooler than they are, so they are both cooling off. If thermal transfer, i.e. transfer of heat, requires a difference in temperature, how much of the small body is exposed to a lower temperature environment as compared to the large body? What do I mean by that? Well, imagine these are both composed of molecules with the same, each one of which is vibrating at the same intensity here. The one on the outside, the larger ball shown here, only the outside layer of material is exposed to a lower temperature environment, right? So the outer layer can cool off because heat is going to transfer out of it into the environment. But the molecules on the inside, represented by the red portion here, are all surrounded by neighbors of the same temperature they are, so they're not going to transfer any heat. So they're going to stay at the same temperature. And it's not until the outer layer cools that heat will then transfer into the outer layer from the inside. But you see how this is going to be a much slower process as compared to the smaller ball, where the same thickness of layer, by the way, it may look like the smaller ball has a thicker layer, but it's not. That's just an optical illusion here. Both of these layers are the same thickness. You see how a higher percentage of the material in the smaller ball is exposed to the environment and therefore can lose its heat as compared to the larger ball. Okay, so I know what you're thinking. What was the point of all that, Spike? Well, because this has implications for origins. If small bodies cool off faster than large bodies, well, we can apply that thinking to bodies in the solar system. Large bodies like, of course, certainly the sun, Jupiter, and Saturn will take longer to cool off than small bodies. Actually, I shouldn't mention the sun there because the sun has its own source of energy. So let's just focus on the planets. Setting aside internal generation of heat, Jupiter and Saturn, being larger bodies, are going to retain their heat longer than smaller bodies. And even among the planets, they are different sizes too. And of course, there's objects smaller than planets. The smallest bodies in the solar system, if they were really billions of years old, and if they don't have internal sources of heat, which the smallest ones do not, They should have cooled off long ago due to this way that heat transfer works. Jupiter and Saturn, not necessarily. They can retain heat for long periods of time. But we can use thermodynamics to look at the smallest bodies and say, are these things warm or cool today? Because if they're warm, this has implications about how old they can be. And for example, our moon, it being a small body that is close to us and easy to study, we see evidence that it is actually not cool inside yet. For example, there's evidence of gas venting from inside the moon, indicating that apparently there's geological activity still going on inside. But what will be the source of energy for this after billions of years? There shouldn't be any left after billions of years. The moon should have cooled off long ago. Apparently, it hasn't done that yet. When this discovery actually was first looked at, people were scratching their heads and actually kind of disbelieving. But subsequently, other evidence for this has accumulated. For example, there's now known to be active tectonic faults on the moon. When this was first announced, people were saying things like this: the whole idea that a 4.5 billion year old body like the moon has managed to stay hot enough in the interior and produce this network of faults just flies in the face of conventional wisdom. Why does it fly in the face of conventional wisdom? Because conventional wisdom says that it's billions of years old, which means, because of thermodynamics, it should have cooled off long ago. But the fact that it's still active apparently means it's still hot inside. And so how is that going to work if it actually is that old? We're also finding fresh volcanic deposits on the moon. And this presents a similar problem. This indicates recent volcanic activity. That shouldn't be happening after billions of years. As a scientist said, this finding is a kind of science that is literally going to make geologists rewrite the textbooks about the moon, because the moon's supposed to be billions of years old and wasn't expected to be still warm inside, but apparently it is. And the moon isn't the only small body that has evidence of heat that shouldn't be there after billions of years. For example, Io, one of the moons of Jupiter, a very small body. It's only about 1.5% of the mass of Earth. Io has some energy being imparted into it from what's called tidal flexing. It's caught on a gravitational tug of war, basically, between Jupiter and some of its neighboring moons. So that's squeezing and flexing Io. And that adds some energy to it. However, Io is much hotter than what that energy should be capable of doing. Io is actually the most volcanically active body in the solar system. It has eruptions blasting material up to 200 miles into space sometimes. At any given moment, there's generally a few active volcanoes going off. Tremendously active place volcanically. Now, this is all attributed to tidal energy, but if you actually look at the numbers, tidal energy can't explain what we see here. It can explain part of it, but not all of it. A large part of Io's heat, its internal heat, is unaccounted for by present-day processes. That would imply this is leftover heat from its formation, but if that formation were billions of years ago, it shouldn't still have that heat today, but it does. Similar argument applies to Saturn's moon, Enceladus. And Enceladus is a really pretty little moon, but it has an interesting thing going on with it. Here's a photograph of Enceladus below Saturn's rings, and hopefully you're able to see in this photograph there's a smudge, or so it appears, beneath the moon. Enceladus actually has, it turns out, fountains, geysers of water and ice coming out of its south pole area. Now, this requires energy to do this. What is it that's blasting this material out into space like this? This is a colorized photograph to bring out details. You can see these are not little sprays. These are huge geysers shooting out of this moon. Well, scientists, again, have said, well, there's tidal flexing going on where Enceladus is being squeezed and flexed. That's true, but this only accounts for a few percent of the energy required for Enceladus to be doing this. Enceladus apparently has a lot of internal heat that is doing this. And where is this heat coming from to produce the effects that we see today? And it turns out the tidal energy prediction actually doesn't even account for the location and how all this is being produced anyway. So since tidal energy only can account for a few percent of this heat that's necessary, it seems that the rest of the heat is left over from Enceladus's formation. Now, if Enceladus were billions of years old, that's a problem because thermodynamics tells us it should have cooled off from its formation billions of years ago. But it hasn't done that. So that would imply it's not billions of years old after all. And one of the more recent bodies in the solar system that we see this at work is Pluto. Now, you might have heard of the discoveries that were made in 2015 when the New Horizons spacecraft flew by. Pluto is amazing in multiple ways. I mean, I have a 20-minute video just on Pluto. But Pluto is apparently resurfacing itself. You see there's a large smooth area here. There's areas of Pluto that have no craters on them. That's because it's been resurfaced apparently not that long ago, because there hasn't been time for any craters to form in these newly resurfaced areas. In fact, as one scientist admitted, this area could be only a week old for all we know, certainly not billions of years. But why would Pluto be doing this? Well, apparently it's still geologically active. Its equivalent of volcanic activity is emitting material that's then covering the surface. The question is, though, where is the source of energy for this? Pluto doesn't have tidal flexing as a possible source of energy, and the other potential sources of heat for it aren't available either. According to secular models, if based on the billions of years idea at least, Pluto should be old, cold, and dead, but it's not. It's geologically active still. And as this scientist pointed out, finding that Pluto is geologically active after 4.5 billion years, there's not big enough typeface to write that in. It's unbelievable. The only potential source of heat for Pluto is primordial heat left over from its formation. If that were billions of years ago, that should have been gone billions of years ago. But there's still heat today. We know that because it's still geologically active today. So billions of years old is a problem. Thousands of years old is not a problem because it could still be cooling off after its creation if that creation is recent. And I'm arguing, of course, that that's what the evidence shows us. So moving onwards, we're seeing some implications of a proper understanding of thermodynamics now. Be more specific then, we talked about heat transfer, what heat is, how it transfers, and some of the implications of that. Let's move more to a specific discussion of the first law of thermodynamics now, which is that heat energy can't be created or destroyed. And I have heat in brackets because initially that was how the first law was understood. Today it is applied more generally. I'll talk about that in a moment. But when scientists first began to study steam engines and how all this works and how can we make it work better, it was realized pretty quickly that you can't create or destroy heat. And this is, not all that brilliant of an insight. It's fairly obvious. I mean, if you want your train and the steam engine in your train to move your train, then you got to shovel coil into the furnace. Did I say coil? Coal, excuse me, into the furnace. If you don't have coal to burn, then your engine's not going to move, right? I mean, that's obvious. You can't get heat out of nothing. It's got to come from the coal. Subsequently now, in modern physics, we understand this more generally. It's not merely that heat energy can't be created from nothing. It's that matter and energy are actually equivalent forms of an underlying reality, if you will. You may have heard the famous equation E equals mc squared. E in this equation represents energy, m represents mass, the amount of material or matter that we have. And c is the speed of light, which is a large number. So that means that a little bit of mass, a little bit of physical stuff, contains a lot of energy. And this is now formalized. The first law of thermodynamics in a modern expression is known as the conservation of matter and energy, that not only heat energy can't be created from nothing, but matter and energy overall can't be created from nothing. They're equivalent forms of the same thing, so you can convert them back and forth, but you can't create either one from nothing. You have to have the other one there to get it from. And that was kind of a convoluted sentence. So let me revisit that. An initial understanding that says energy can't come from nothing, you have to get it from some physical stuff, is now in a broader sense understood that you can't create either matter or energy from nothing. You have to have the other one to get it from. So matter and energy being equivalent, as I showed in my last slide, means we can convert them back and forth, but we can never get either one from nothing because that violates this law of physics. Okay, so what do I mean by convert back and forth? So you can get energy from matter, and the most efficient way we know how to do that is a nuclear explosion. I mean, a little bit of stuff converts into a lot of energy, right? We can go the other direction too and take a lot of energy and convert it to a little bit of stuff. And we do that at particle accelerators. We get little chunks of matter zipping around close to the speed of light, smash them together. More material comes out of collisions than went in. And I don't just mean the number of particles, I mean the amount of matter coming out of the collision. But did we create the matter from nothing? No. We converted the particles' kinetic energy, their energy of motion, into matter. So my point is, you can get matter from energy, and you can get energy from matter, but you can't get either one from nothing. You have to have something that you're converting it into. If you're going to say that we can get either of those things from nothing, well, now you're violating the first law of thermodynamics, which is a very fundamental part of physics now. And so far, I'm presenting this as a law of physics. We actually see this in our everyday experience. It's very common in our lives. For example, why do we need food every day? Hopefully every day. Well, because our bodies need energy to function, can't make it from nothing because that violates this law of physics. So we have to get it from the chemical energy stored in the food. And of course, we have to get it in our mouths first, which is maybe a little more difficult sometimes. Why do we get bills and invoices from the power company every month? Well, because our appliances need energy to work, can't get energy from nothing because that violates this law of physics. So we have to get it from the power company, which also can't get it from nothing because that would violate this law of physics. Power companies get it by converting chemical energy from coal into energy, or perhaps the gravitational potential energy in flowing water and hydroelectric energy, or even perhaps solar energy and getting it from the sun. And of course, the sun also can't make it from nothing because that violates this law of physics. It has to burn hydrogen and helium through fusion and so on. So not to belabor the point, but this is a very fundamental law of physics. You can't get matter or energy from nothing. You can convert one to the other, but you can't make either out of absolutely nothing because that violates this law. And in fact, this presentation wouldn't be possible tonight if this law weren't true, because some of the principles of circuit design and the computer that you're watching this on are based on this law of physics. And if you've ever taken a physics class, you know how fundamental this law is. One of my textbooks says that conservation laws, this conservation of matter and energy that we're talking about, are the guiding principles of physics. These are absolute conservation laws. They are always obeyed. So why did I spend so much time talking about this? Because this law has implications for origins. Specifically, where did the universe come from? If you're going to propose a model where something came out of nothing, then you are violating this law of physics, aren't you? Because if you're saying that at first there was nothing, at one point there was nothing, and then suddenly there was something, and then over time that something developed into the universe that we see today. If you're going to propose that as an explanation for why we are here, well, you're violating the first law of thermodynamics right at the beginning of your model, aren't you? Because everything can't come from nothing. You're violating this law on the largest possible scale. I mean, if you were taking a physics class and solved a homework problem or a test problem in such a way that violated this law, your answer is automatically wrong. But think about a cosmological model that does this. I mean, it's violating this law on the largest possible scale. It's saying that everything came from nothing. But that's not true because this law of physics doesn't allow that. Now, there are multiple ways in which you can propose a model that's based on this false idea that something came from nothing. The first law of thermodynamics is useful because it disproves this entire category of cosmogonies, and cosmogony is a cosmic history. So there's different ways that various people have tried to explain how the universe could have gotten here from nothing without a creator being involved. But we see then that this very fundamental law of physics doesn't allow that to be true. What about the second law of thermodynamics? Let's talk about that a bit. Now, you may have heard the second law expressed as entropy in a closed system will always increase. But as we've already said, the concept of what entropy is a little fuzzy, and a lot of people get this wrong. So a more accurate definition is that entropy change is the measurement of how more widely a specific quantity of molecular energy is dispersed in a process. Well, that's a real mouthful. What does that mean? Well, it basically means that a concentration of energy, given the opportunity, will disperse and become more widely distributed. For example, think of what happens when you put wood in a fireplace. You have a lot of chemical energy trapped, if you will, or in the wood, or encapsulated, maybe a better word, in the wood. And then when you ignite it, what happens? That energy is released in the form of heat and light and some other things. And where does all of this stuff go? Well, the light, of course, comes out into the room. The heat comes out into the room. Some of it goes up the chimney stack and heats the atmosphere and ultimately escapes into space. Some of it is not converted to energy directly, but like particles, smoke and such, that dissipates too. If you start out with a chunk of wood that you can hold in your hand, ultimately the energy in it is going to be released into the atmosphere and then ultimately in space. You can see then what starts out as a local concentration of energy will, given the opportunity, disperse into a much broader distribution, if you will. So this is the second law at work. Concentration of energy, given the opportunity, will disperse and become more widely distributed. Now, this has some important implications. Like, for example, it means that hot things cool off. Wow, that's a brilliant observation there, Spike. We're so glad we came to your talk tonight. Well, no, actually, this is an important observation because it has implications for origins. For example, if hot things cool off, let me get my slides organized again. We see, pardon me, I'm looking at my slides here in two different places because Zoom isn't showing me ahead of time. If hot things cool off, we can apply that in a broader sense than just what our everyday experience has. For example, hot cup of coffee sitting on the table. You walk into the room, you see the coffee. How long has the coffee been there? A long time or a short time? Well, thermodynamics allows us to use coffee as a form of clock, essentially. If it's still hot, then we know it hasn't been there very long, because had it been there a long time, it would have cooled off a long time ago. The fact that it hasn't done that yet means it hasn't been that long. So in a broader sense, you can ask the question, has coffee, could a hot cup of coffee have been there forever? And the obvious answer is no. Had it been there forever, it would have cooled off forever ago. Well, we can use that same kind of logic and apply it to the universe. Is there anything in the universe that hasn't cooled off yet? And the answer is yes, stars. Can stars have been there forever? No, because had they been there forever, they would have cooled off or blown up forever ago. Whether they cool off or blow up, individual stars vary in what happens to them. But the point is, in regardless of their individual fate, all of them as a class would have been gone forever ago if the universe had been there forever. The fact that we still see stars tells us that the universe is not eternally old. Because if the universe had been there forever, then stars would have cooled off forever ago. But they're still there today. Now, some people would say, well, wait a minute, new stars can form. There's actually some problems with that idea from a secular perspective. But setting those aside, star formation still requires a source of energy, of which there's a finite amount available in the universe to power it. So had the universe been there forever, there would no longer be energy available today for stars to form. So point is, had the universe been there forever, we wouldn't see stars anymore because the ones that exist would have burned out. New ones couldn't have formed forever. That would have stopped forever ago as well. But again, we do still see stars today. That answers the question for us then, can the universe be eternally old? The answer is no. Applying the second law of thermodynamics to the universe shows us that it can't be eternally old. It has not been there forever. And if it's not eternally old, what does that tell us? It means it had to have had a beginning. Sometimes Christians endorse the Big Bang model and say that we need the Big Bang model because it shows how the universe had a beginning, and that's consistent with Genesis. Actually, the Big Bang model is not consistent with Genesis. That's a broader topic. My point for right now is that we don't need the Big Bang model to show that the universe had a beginning. If you want to prove that the universe had a beginning, just walk outside and look up. Do you see a sun during the day? Do you see stars at night? Yes. Well, if so, that proves every day, it reminds us that the universe had a beginning. So moving onward then, we talked about how the first and second laws of thermodynamics work, and we talked about some other implications for origins. Now we have more tools in our toolbox, so to speak. We're better equipped to go back and revisit some of those misconceptions that we started the presentation with. So let's talk about some of those and go back and correct them. The statement that evolution is impossible because it's a decrease in entropy, now that we have a better understanding of what entropy is, first of all, we see that that's flawed also. There's also a problem with this particular statement because the Earth is not a closed system. And the argument from entropy only applies to systems that are closed, and closed means energy can't come in or out from an external environment. The Earth receives energy from the sun. So this argument is flawed in actually two ways, not just one. Number one, increasing entropy does not mean that it's not associated with organization and disorder like we talked about. Second of all, because the Earth does receive energy from the sun, you couldn't apply the second law to the Earth in isolation anyway. So that's why this argument shouldn't be used. What about the argument about oil and vinegar? That's actually not a reversal of entropy. If you look at the separation of the two, that's a lower energy state, and thus entropy increases when they separate. So if you're going to simplify things incorrectly and say that increasing entropy means quote unquote order can never increase, that's wrong, because what we perceive of order, what we perceive as order does not necessarily correspond to how entropy is changing. Same thing with crystal formation. Crystals, as they form, actually represent an increase in entropy, not a decrease. That's why this process can happen on its own. And the same thing with babies growing. Babies growing do not represent a reversal of entropy. What about the fall of man? Is this actually the source of the second law of thermodynamics, as some have said? Well, I don't think so, for a couple of reasons. Number one, the second law of thermodynamics is actually important in a lot of physical processes. For example, when you digest food, that's an increase of entropy overall. So could Adam and Eve digest food before the fall? Well, apparently, because they were told, here's the garden, here's all the food, you can eat everything except from the fruit from this one tree. Well, that sort of implies that if they could eat all this fruit, that they could digest it as well. So if digestion was functioning before the fall, then the second law of thermodynamics was functioning before the fall as well. Also, we know that Adam and Eve walked in the garden. Well, walking actually requires an increase in entropy, which is the second law at work, because it requires friction between your feet and the surface that you're walking on. Since Adam and Eve were apparently able to walk, that too would indicate that entropy was increasing and that the second law was at work. So if that's the case, then what changed at the fall? If the second law was already in place, then what happened at the fall? I mean, we tend to think of the second law being responsible for decay and deterioration, as we've seen in some of the quotes already. The Bible doesn't tell us specifically what changed, but I would argue that one possibility is that God's divine sustenance, his sustaining of the creation, was removed at least partially at the fall. For example, when Israel was in the desert for 40 years, the Bible tells us that their clothes didn't wear out and their sandals didn't wear out. Normally, those things would happen. I mean, we know that the sandals still had friction against the desert ground, or against the ground, because they were able to walk for 40 years. But nevertheless, their sandals didn't wear out, which they would normally do. Apparently, that's because the Lord was sustaining them divinely. So that's a hint, perhaps, that what happened at the fall was God was allowing the second law to operate in some ways, but sustaining the creation against the deterioration implications that would normally have resulted. When the fall happened and the curse was imposed, my understanding would be that his sustenance that he had previously been granting was removed. And so not only now is the second law operating, but also some of what we would perceive as harmful effects also operating as well without his divine sustenance. So that tells us how we shouldn't use the laws of thermodynamics. And we talked a little bit about some valid arguments instead. Let's talk about some additional ways to correctly apply laws of thermodynamics. One of them is the origin of life. Thermodynamics is actually applicable here. For example, you may have heard of origin of life studies where those who are trying to show how life could have gotten here without a creator are trying to show how life can form by itself from non-living chemicals. Well, to do that, you need proteins, and to make proteins, you need amino acids. And it's interesting because when you manufacture amino acids in the laboratory, you run into an issue called chirality. Amino acids, in life at least, are all left-handed, so-called because of the structure of the molecule, as you can see here, kind of resembles the left hand. Now, when you make amino acids in the laboratory, they're actually a mixture of left-handed and right-handed versions. But life is exclusively made from the left-handed form. So if life came from just a batch of chemicals, often some warm pond somewhere, presumably it would be made out of the mixture of amino acids that would be made in a non-living environment from whatever process you're proposing. But that's not what it looks like. If you try to make proteins out of a random collection of amino acids, you're going to get a mixture of left-handed and right-handed amino acids all jumbled together. And that doesn't work, by the way, for life. As I said, life is exclusively left-handed. Not only that, when researchers have tried to construct an apparatus in the laboratory that filters out and separates the left-handed from the right-handed so that they have an exclusive collection of left-handed amino acids to try to make something from, for thermodynamic reasons, some of the left-handed amino acids will spontaneously change into right-handed amino acids. So one of many, many problems with origin of life research, again, trying to disprove the idea of creation, is this chirality issue based on thermodynamics, where you can't get the right structure of amino acids to make your proteins and then to make anything from. Another area where this applies is DNA. DNA is a very complex molecule and fairly delicate, but the cell actually has a lot of mechanisms to repair it over time. Left to its own devices, DNA will decay as a result of increasing entropy, thermodynamics again. And this actually happens fairly quickly. In fact, a study was done a while back that talked about how quickly will DNA decay in bone. And they found out that even if you take your sample of tissue, even if you freeze it and seal it off from oxygen, I mean, these are the best possible conditions to preserve something. They found out that DNA would still spontaneously decay because of thermodynamic reasons on its own. And doing the math on this, they figured out that every base pair in DNA would rupture and break after 6.8 million years. Now, that sounds like a long time, and it is a long time, of course, but it has implications that anything more than just a few million years old shouldn't have intact DNA in it anymore. Now, again, this is the best possible case when you freeze the tissue and seal it off from air. If there's bones buried in the ground somewhere from some animal that died at some indeterminate time in the past, obviously that bone is not frozen and it's not sealed off from the environment. So the DNA in it will decay even much more quickly than that. But set that aside for the moment. If every base pair of DNA should be broken after just roughly 6.5 million years, well, the last dinosaur supposedly died 65 million years ago. That's 10 times the period of time in which all the DNA would be gone. But there's evidence for intact pieces of DNA in dinosaur tissue, thus indicating, based on this argument from thermodynamics, that dinosaurs actually didn't die 65 million years ago. They're actually much more recent than that. And of course, if you've been around the creation movement for a while, you've also heard about dinosaur soft tissue. intact bone proteins and other things that shouldn't be there if these creatures really died millions of years ago. Moving out to a broader picture now, a broader way to apply thermodynamics, we run into one of my favorites, which is called the secular dilemma. Now, what is a dilemma? A dilemma, I'm saying in a second. A dilemma is a choice between equally unfavorable alternatives. So there's something that I call the secular dilemma because there's a basic question here. Did the universe have a beginning? Now, that's a simple question. It's only 6 words long. How many possible answers are there to this question? Well, if you think it, there's just 2, right? There's yes and there's no. So if the answer was yes, then yes, the universe had a beginning. If the answer is no, it didn't have a beginning. Why am I calling this a dilemma? Because if you're going to construct, or if you're going to propose a history of the universe, a cosmology, you have to answer this question fairly early in your thinking, right? And if you're going to try to propose a secular cosmology, one without a creator, then, as we just said, you only have 2 choices, yes or no. It turns out both answers, both potential answers, violate thermodynamics and the laws of physics, therefore, in a different way. So whether you pick the yes answer or the no answer, you're going to violate physics because of these laws of thermodynamics that we're talking about. What do I mean by this? Well, okay, let's look at the yes answer. If you're proposing the universe came into, is here without a creator, and you answer yes to this question, then yes, the universe had to have a beginning. Well, if the universe is everything, right? That's what the word means. So if everything had a beginning, then what existed before the beginning? Well, the answer has to be nothing, because if everything began, then before the beginning, there couldn't have been anything. Because if there was something before the beginning, then whatever began wasn't really the universe, because it was no longer everything, right? Because there was already something before it. So if you're going to say the universe had a beginning, then you had to say that at some point there was nothing, and then subsequently, for some reason, there was something. So some versions of the Big Bang model actually say that there was nothing, and then the universe popped into existence from nothing. Here's actually a graphic of what the universe looked like before the Big Bang, according to this thinking. So this, of course, is nothing. Of course, this is only an artist's conception too. But does this really make sense? Can nothing make everything? Can everything come from nothing? Well, no, because nothing can create what? Nothing. Nothing can do nothing. And from nothing comes nothing. You can't go from nothing to everything. You can't go from nothing to anything, can you? Based on, as we talked about, the first law of thermodynamics, mass and energy are conserved. The total amount never changes. So you can't create either one from nothing, like we've already talked about. So thermodynamics tells us something could not have come from nothing. Now, there are claims that it has. For example, Dr. Lawrence Krauss's best-selling book, A Universe from Nothing. You would think by the title that this tells us that something can come from nothing, and it tells how the universe did come from nothing. But if you read the book, it's actually not what he's saying. He addresses us actually fairly early in the book when he says, now you might be expecting me to say how the universe came from nothing. Well, my version of nothing is a little bit different than how most people view the word. When he says the universe came from nothing, he really means the universe came from an empty vacuum of space with permeated with quantum fields that were capable of producing particles. Well, that's not nothing. That's certainly something. So despite books like this with titles that imply something could come from nothing, that's actually not true. So back to our dilemma, if you're trying to build a secular cosmology without a creator, and you say that, yes, the universe had a beginning, well, the first law of thermodynamics doesn't allow that to be true. So you're going to violate the laws of physics with that proposal. So your only other option then is to answer no. If the universe couldn't have had a beginning, then it must not have had a beginning. Therefore, it must be what? Eternal. But we talked about this already too, didn't we? With the second law of thermodynamics. We saw that how things cool off. we saw that heat energy is still unevenly distributed in the universe because stars still exist. I mean, think about the universe. There's very hot stars surrounded by vast expanses of cold space. The heat in the universe is still very uneven. But the second law tells us that over time, it wants to even itself out and distribute itself out equally. And again, since it hasn't done that yet, just like the coffee didn't cool off means it hasn't been there forever. Since the universe is still unevenly distributed with the heat energy it contains, it hasn't been there forever either. Now, some will argue, well, wait a minute, there's one way in which there can always have been something. This is called the oscillating universe, where there were the Big Bang, and then expanded for a while, then the universe contracts under gravity and has what's called the big crunch. And then the crunch rebounds and makes another big bang. And so you go bang, crunch, bang, crunch, bang, crunch, oscillating forever. That doesn't work either. Among other things, if we've talked about entropy always increases over time, if the bang produces an expanding universe, well, first of all, today's Big Bang model doesn't match this anyway, because it says the expansion is accelerating, not slowing down. But second of all, thermodynamics shows us this overall idea can't work either, because if you go from bang to an expansion and entropy is always increasing, well, that means this condition has higher entropy than this condition did. That being the case, you can't go from this one back to that one, because that requires a reversal of entropy. It basically requires time going backwards, because entropy is closely associated with the passage of time. So thermodynamics shows us that the oscillating universe doesn't work either. Basically, it's an argument, more than an argument. It shows us that the universe can't have been there forever. It can't be eternal. Well, if the universe can't be eternal, then that takes the no option off of the table too, doesn't it? And those are the only two options that the secular thinker has for a cosmology. So again, the secular dilemma, did the universe have a beginning? If the secular thinker says yes, he violates laws of physics in one way, based on thermodynamics. If he answers no, he violates the laws of physics in a different way, also based on thermodynamics. There is a third option for this, and that is that the universe did have a beginning, and we know that because it hasn't been there forever, but a supernatural creator brought it into being, thus avoiding a violation, of the first law of thermodynamics. So a supernatural creator is the only option, the only potential cosmogony, history of the universe, that doesn't violate these laws of physics. Because if you think about it, there's only three logical possibilities for why the universe exists. Either it was formed by a creator, or it formed without a creator, or it never formed at all, it's always existed. I mean, those are the only three possible options, right? We saw that it can't have formed without a creator, because that would violate the first law of thermodynamics. It can't have always existed, because that violates the second law of thermodynamics. So the only logical option left is that it was formed by a creator. So thermodynamics allows us to prove that any atheistic cosmogony, any atheistic proposal for how the universe or why the universe exists, is not allowed. All of the possible explanations from a secular perspective without a creator are going to violate the laws of thermodynamics and thus the laws of physics overall in one way or the other. And this is a great conversation starter, by the way. I mean, a lot of times people want to know, how can I really share creation with other people who haven't heard this stuff before? If you have the opportunity to show them photos, I'd personally start with dinosaur soft tissue. I find that's really effective. But if you have someone who's more philosophically minded and likes talking about interesting ideas, ask them the question, did the universe have a beginning? What do you think? And then depending on which possible answer they pick, show them how that answer without a creator winds up running into the laws of physics and not allowing that possible answer. And show them that without a creator, they're going to wind up violating physics and they're thinking one way or the other. Now, this question isn't going to work on everybody. Some people will find it interesting, some won't. I know it'll work on some people because it worked on me. This is actually the question that got me on my journey away from atheism and trying to figure out a way to avoid this trap. How can the universe be here on its own without a creator? And at the same time, not violating the laws of physics in my thinking. I would also argue, and the Bible doesn't tell us this specifically, but I think maybe it's a valid conclusion. I would also say that this is evidence of God's grace, this particular aspect of thermodynamics and the universe. You know, the Lord didn't have to create the universe in such a way that that he did. He could have created the universe in such a way that there's a possible explanation for it to be here without him, but he didn't do that. In our weakness, how many of us would struggle with believing in faith by creation if there was a valid explanation outside of creation? I mean, how many of us would struggle with that? The Lord didn't make things that way, though. He created a universe that looks created, and this fascinates me. The laws according to which the universe operates also show us that he's responsible for that universe existing. And I think that's just fascinating. So I would actually view that as evidence of God's grace. Again, he could have made the universe any way he wanted, but he chose to make it in the way that he did, where as we understand more about how it works, we see more and more evidence for his creative handiwork throughout. And I just love that. So in our session so far, we've talked about some misconceptions. We talked about how the laws of thermodynamics work, how the first and second laws work anyway. We talked about some misconceptions. Now let's move on forward to our last section and discuss why the laws work, and see what further insights we can get from that. So why does the second law of thermodynamics work? Why does entropy increase? I mean, we've talked about what entropy is, and it's associated with energy distributing itself over time. Why does that happen? Well, at first that wasn't understood, but scientists like Ludwig Boltzmann, late 1800s, early 1900s, started to look into this and eventually figured this out. Now, I don't want to get people lost in mathematics here, so I'll try to use some concepts that are more familiar to us. Let's talk about the heat distribution, or the distribution of heat in the room that you are currently sitting in. I assume no one's watching this from outside somehow. So if you're sitting in a room, imagine mentally that the room you're in is divided up into 6 zones, 6 spaces within the room. And let's talk about a calorie of heat. If there's 6 possible zones, then the calorie of heat could be in any one of the 6, right? Let's represent its position with a die. So if you have 1 calorie of heat, the number on the die will represent which of those 6 zones in your room that the calorie of heat is in at the moment. So if you have 1 calorie of heat, we can represent that by 1 die. There's 6 possible positions, and you can imagine when you roll a die, you can get 1 through 6, with equal possibilities. So there's equal odds of this 1 calorie of heat being in any of the 6 regions in your room. Now, I know this, you're probably wondering where I'm going with this, but hang in there. It'll make sense in a moment, I hope. So if there's only 1 calorie of heat, there's equal odds of it being anywhere in the room. And I'm setting aside things like thermal currents and other things, just to simplify a bit. What if there's 2 calories of heat? Well, now you need to represent their location with 2 dice. How many of the 36 possible combinations represent both calories being in the same zone, right? So if there's 2 calories of heat, you got 2 dice to represent them. Roll the dice, you get 36 possible numbers. How many of those, though, represent results where both calories are in the same region? And there's only 6, right? So out of the 36 possibilities, the odds of both calories being in the same region in the room is only 6 out of 36, which is 1 out of 6. So you see that because you have more calories, the odds are getting less random, if you will. What do I mean by that? Well, if there's 3 calories in your room, the odds of them all being in the same region is now down to 1 out of 36. If there's 4 calories, the odds are 1 out of 216. 5 calories, the odds of them all being in the same region are 1 out of 1,296. The numbers grow really rapidly. The more calories of heat you have, the much more difficult it is for them to all be in the same region in the room. Hopefully this is making sense, and it's difficult to do this over Zoom where I can't see people's faces like you can with a live audience. But the point is, the more calories of heat you have, the less and less likely it is that they're all going to be concentrated in one corner of the room, let's say. On the other hand, the odds become overwhelmingly large that they will be distributed more evenly in the room. And this is why hot things cool off, is because when you start out with a system with a hot cup of coffee sitting on the table, there's more calories of heat inside the coffee, a higher concentration compared to the overall environment. But all the possible ways to arrange calories in the room, there's many, many, many more possible arrangements where the heat calories are more evenly distributed compared to them all being concentrated in the cup. So when you put a cup of coffee on the table, you're not worried about it pulling all the heat in the room into the cup, and so the coffee starts boiling and the rest of the air starts freezing. No, that doesn't work that way. It goes the opposite direction, right? Heat distributes itself evenly because there's so many more ways to have the system of an even distribution of heat compared to an uneven distribution of heat. And I apologize that that seemed tedious, but there's a point here. The more and more you have, in this example, calories, the more extreme the odds get against them being concentrated. So again, that's why the second law works. That's why heat energy distributes itself over time. In fact, energy overall will distribute itself, given the opportunity. So what's the point of all this, Spike? Well, the point is, we can use this kind of reasoning to calculate the mathematical probability of ways that matter and energy are arranged. And this actually is a fairly powerful tool, especially when it comes to origins. A low entropy system, therefore, represents a system that is less probable. And a higher entropy system where the energy has distributed itself is more probable. So now we can mathematically measure the entropy of a system, and now we see that it corresponds to the probability of that particular arrangement of the system existing. So a low entropy system is very improbable. A high entropy system is more probable. Guess which of these two options today's universe is? Low entropy or high entropy? Turns out the universe today has very low entropy. This means the universe is mathematically improbable to be in the condition that it's in, the arrangement that it's in. Moreover, second law of thermodynamics tells us entropy always increases. If it's been increasing through cosmic history and it's still very low today, that means it started out very low in the beginning because it increases over time. Excuse me. So applying this thinking to the universe overall, even if something could create itself from nothing, which we already said is impossible, but secular thinkers want to believe that it is possible, even if that were possible, our universe is still extremely unlikely to have been the result of a random unguided event like that. If you're going to try to invent an explanation where the universe came into existence by itself without a creator, then presumably it would look like a random, like the result of a random process, an undesigned process, because there was no designer involved in your proposal. But the universe doesn't look that way. The universe looks extremely improbable still. And if it's still low entropy and thus improbable today, if the universe is 14 billion years old, almost, according to their model, and if it's been increasing in entropy this whole time, entropy was extremely low at the very beginning. And this brings us into a paradox, a problem that secular thinkers have with their billions of years cosmogonies. And to illustrate this, I had kind of a weird analogy. Let's say someone came up to you and said, I was trying to think about where Washington, D.C. came from. There's the city over in the east, and I think I figured out how or why this city exists today. I believe that this city popped into existence from nothing. And you say, that doesn't work. Cities don't pop into existence from nothing. And the person says, well, I think that they can, and I think that this is a good explanation for where the city came from. So you're trying to illustrate to your friend how silly of a proposal this is. And you say, wait a minute. So the city of Washington, D.C. contains buildings, it contains people, there's several museums there, there's exhibits within the museums. You're saying that the whole city popped into existence complete with people and all the rest of it from nothing. I can say it's actually much easier for a subset of that to have popped into existence. For example, I can say that the Declaration of Independence, the original one, popped into existence from nothing, complete with the parchment and all the signatures and all the rest of it. That is far more probable to have popped into existence on its own than the entire city would be, right? Even if it's still a silly idea, of course, for it to have done this. So to illustrate to your friend how ridiculous that idea is, you take a much easier proposal and say that it's still ridiculous. Therefore, how much more ridiculous is his proposal that the whole city happened? Well, why do I come up with this weird analogy? The Big Bang universe, or the universe according to the Big Bang model, would have been so improbable, according to the model itself, that something else happening instead is far more probable. This is called the Boltzmann brain paradox. And the name you might recognize, Ludwig Boltzmann, that I mentioned earlier. He didn't propose this particular problem, but it's arisen from the mathematics that he discovered. The Big Bang, having produced our universe that we're in today, is so mathematically improbable that it's far more probable that the only thing that got created was your brain. Your brain popped into existence from the void a few seconds ago, complete with all the memories that you have in your head. Now, you may think that you had a childhood, you grew up, and you had this life until today. You remember all of that. Those memories are actually all false because your brain had to pop into existence with the molecules arranged somehow, and it just so happened they're arranged in such a way to give you these false memories. And you think you're perceiving the universe around us, but that's false too. That's part of the illusion. Your brain was just formed that way with this false sensory input. Not that any of this really matters, because you're going to dissolve back into the void here in a few seconds anyway. But as silly as this idea is, it's actually far more probable to be the case mathematically than for the Big Bang to have made the universe that we live in, because of this argument from entropy. And if you haven't heard this idea before, it's really, of course, very strange, but it's actually out there. As this article in the New York Times said, this could be the weirdest and most embarrassing prediction in the history of cosmology, if not science itself. If true, it would mean that you yourself are more likely to be some momentary fluctuation in a field of matter and energy out in space than a person with a real past in an orderly star-spangled cosmos. Your memories and the world you think you see around yourself are illusions. This bizarre picture is the outcome of a recent series of calculations that take some of the bedrock theories and discoveries of modern cosmology to the limit. The basic problem is that it's hard for nature to make a whole universe. It's much easier to make fragments of one, like planets, yourself maybe in a spacesuit, or even, in the most absurd and troubling example, a naked brain floating in space. Nature tends to do what's easiest from the standpoint of energy and probability, and so these fragments, in particular the brains, would appear far more frequently than real full-fledged universes, or than us, or they might even be us. Alan Guth, a cosmologist at MIT, and by the way, he's a rock star in cosmology if you're not familiar with his name, who agrees this overabundance is absurd, pointed out that some calculations result in an infinite number of free-floating brains for every normal brain, making it, quote, these are his words, infinitely unlikely for us to be normal brains, unquote. So getting back to the analogy I did, someone says that a whole city popped into existence and you say that's ridiculous. And to help you understand why it's ridiculous, it's much easier just to make the Declaration of Independence pop into existence from nothing. That's not going to happen, but it's still far more likely than the whole city popping into existence. This holds true for the Big Bang model. It is so mathematically unlikely for the Big Bang, assuming that something could come from nothing in the first place, which we've already said is impossible. But even if you grant that, our universe is so mathematically unlikely that it is far more likely that if something did pop into existence, it was only your brain. And I say your brain because you're sure that you exist, right? I mean, you're thinking. You don't really know that anybody else exists or that the world exists. You're relying on your senses to know that. But this says that it's actually far more likely that your senses are not operating correctly. This whole thing is an illusion. So this is called the Boltzmann brain paradox. And just to clarify, this is not to say that your brain is floating in the cosmos by itself. There is no cosmos. It's just you. You are the only thing that exists. Now, I know what you're thinking, and the question that you're wondering is, the answer is no. Noah Spike isn't actually making this stuff up. This is actually a problem in modern cosmology. And you can find papers on this. As this one said, a typical observer in the multiverse, the multiple universe idea that's popular in secular cosmology today, typical observer in the multiverse is a Boltzmann brain. In the eternally inflating vacua, observers are infinitely more likely to be Boltzmann brains than honest folk like ourselves. This paper said the most likely fluctuation, consistent with everything you know, is simply your brain, complete with quote-unquote memories of the Hubble deep fields, WMAP data, etc., fluctuating briefly out of chaos and then immediately equilibrating back into chaos again. This is sometimes called the Boltzmann brain paradox. This paper was about avoiding Boltzmann brain domination in holographic dark energy models. A note on Boltzmann brains, sinks in the landscape, Boltzmann brains on the cosmological constant problem. I like this one. This one said, can the Higgs boson save us from the menace of the Boltzmann brains? I mean, this, of course, this title is meant to be humorous, but the point is that cosmologists actually struggle with this. Boltzmann brains in the scale factor cutoff measure of the multiverse. Now, for a while, they actually thought they had solved the Boltzmann brain problem, but then they realized that the solution was incorrect, as announced by papers like this one, the return of the Boltzmann brains. So what does all this tell us? I mean, if you're going to be a secular cosmologist, we already saw that you have to violate the laws of physics in your model based on the secular dilemma. But even setting that aside, if something did somehow come from nothing, what does secular cosmology actually predict? Does it predict that a universe popped into existence, or is it just a brain? Well, the mathematics tells us that the brain wins. The logical outcome of secular cosmology, by its own mathematics, says that the universe doesn't exist, that you are just a brain floating in the void. So what does this mean? Based on these arguments from thermodynamics, the Big Bang model says that you're actually a Boltzmann brain. You're a naked brain floating in the void. That means there's no universe. And if there's no universe, then there was no beginning of the universe, which means that the Big Bang never happened. So the logical outcome of the Big Bang model is that the Big Bang itself didn't happen. The model disproves itself. So secular thinkers often claim that science gives us this great weapon to use against Christianity and the Bible. But in reality, the only weapon that science gives them is this one. Their model is self-refuting. It disproves itself. If it's true, it's false. Therefore, it is false. So we saw then more implications for origins that thermodynamics gives us. We talked about some of the misconceptions, some of the bad arguments that we shouldn't be using. We talked about whether the second law came into existence at the fall. I don't think it did. I think the fall was just a removal of God's divine sustaining, his sustenance of the creation. We talked about whether entropy is an increase in complexity and how that's actually misconception and incorrect arguments that can arise from that. We talked about various misconceptions here. First law of thermodynamics, the idea that energy and matter can't be created or destroyed, you can only convert them back and forth, has implications for origins. The process of heat transfer has implications for, among other things, heat transfer, the age of astronomical bodies. We talked about how thermodynamics affects origin of life. DNA decay shows us that various animal tissues apparently are not very old, which indicates these animals weren't alive billions of years ago. We talked about the Boltzmann paradox, which to me, at least, is really illustrates the ultimate absurdity of any secular model of origins because it denies that reality even exists. But that's the logical and mathematical outcome of their way of thinking, which shows us that their way of thinking must be wrong. And I think it's interesting too that all of this ultimately came from an endeavor how to make steam engines work better that had a commercial motive. People started looking into all this from the desire to make more money. And what started with commercial intent ultimately reveals truths about our origins. And I say this one for last to emphasize it. We talked earlier about the secular dilemma. If there's anything you take away from this presentation, I hope it's this. Again, a simple 6-word question: Did the universe have a beginning? Talking to people and get them to think about the implications that there's only 2 possible options, and how thermodynamics shows that neither of those options are going to work if you deny the supernatural creator. The supernatural creator is the only way to have the universe without violating a law of physics in your model. And since presumably we want our scientific models to concord, to be in concordance with the laws of science themselves, then therefore physics tells us that there is a supernatural creator. So that is how thermodynamics confirms creation. Hopefully this has been an interesting way to look at things from perhaps a different angle than is commonly discussed in creation circles. If you like this way of looking at things, my website is creationastronomy.com. There's a variety of articles there. By the way, 2 days ago, I just published a big article on the James Webb Space Telescope and some of the first discoveries and results from it. Really, really fun stuff there. If you're interested in astronomy specifically, that available to you. There's also a sign-up form at the bottom of every page for my email newsletter. This is free. Only comes out a couple of times a year currently. I'm hoping to improve on that. But my point is you won't be spammed to death. But as new things are announced and new discoveries are made in astronomy, that is what that newsletter is for. You will also see several DVDs being offered there. Some of you are probably familiar with this already, that I offer a currently 3-volume set, hopefully soon to be a 4-volume set on astronomy from a creation perspective. You may or may not be familiar with volume 1 of the series being the solar system. This one goes planet by planet through the solar system and talks about how each one discredits a secular origins model in a different way. It's a lot of fun, very visual presentation, lots of photographs and animations and graphics. Some of you, I'm sure, have seen this already. What you might not know, though, as I said, it goes through every planet, talks about the origin and age. What you might not know is that I updated this in May of this year to include results from recent missions, a lot more information than was previously in that one. In fact, this is now a 2-DVD set. It wouldn't even fit on 1 DVD anymore. So if you have seen volume 1 and have an older edition of it, older being before May of this year, you might want to look into getting the new one because there's newer information. And if I dare say so, much better than it was before. I've significantly upgraded the graphics. In fact, if you are comfortable with online video, either downloading or watching something online, I would recommend the digital version to you because that's now available in high definition, whereas before it was only standard depth. Volume 2 in the series is talking about stars and galaxies, design arguments from the sun. A lot of people don't think about, is our sun designed? Well, yes, it is. There's evidence for that. Where do stars come from? Where do galaxies come from? What does the cosmos overall tell us about our creator? Volume 3 is about the Big Bang model. Where did the universe itself come from? The overall idea of cosmic origins. Is there evidence for a Big Bang? Well, actually, no, the Big Bang is not only not a bad scientific model, it's anti-scientific. It denies some of the requirements of science. The secular dilemma that we talked about comes out of volume 3, including the Boltzmann brain paradox, but there's a lot of other stuff there too. That's a 2-hour video overall. So you've heard a few items from it tonight, but there's more there where that came from if you like that kind of thing. So what do the heavens declare anyway? They don't declare the glory of the Big Bang model. Science does not declare the glory of how this all got here without a creator. No, the heavens declare the glory of God. And thermodynamics is only one aspect of how we can perceive more of God's glory through science. And I hope this has been interesting for you here this evening. And this concludes my presentation.
All right.
That's really, really good. Where do we get that James Webb Telescope information?
If you go to creationastronomy.com/articles, it is the top one on the list.
Thank you.
Okay, and then so you did list a lot of different videos that you have available on creationastronomy.com.
Yes.
A couple of people and of course this talk that you're doing tonight will be on our Facebook page, and we're going to be posting it to our 3 channels, BitChute, Rumble, and YouTube. But some people have asked if you have this talk available on DVD.
This talk is not yet on DVD. Before I create a video and commit something to video, so to speak, I like to give it live for a while to experiment with different ways of talking about concepts and seeing, what really resonates with people. So that's one of the reasons I'm doing this tonight, is to try out this talk and see how people respond to it. And if I was concerned when I first thought about this subject that it would be too narrow and too geeky, if I can make an adjective there. So I'm curious to get people's feedback if they think it's still interesting or if it was too technical or too weird.
Well,
Yeah, that makes sense. So we are kind of over time, but we want to ask you just a few questions. So there's quite a few questions in the comments, but if we could get you to answer just maybe a couple, maybe we'll choose 2 or 3 questions, if that's okay
Sure.
with you. Okay, so
give me the easy ones and then you answer the hard ones.
oh, well, I don't know about that.
Not an option.
Vince asks, Spike said that DNA would be destroyed by 6 million years, and then pointed out that dinosaurs are reported to have died out at 65 million years, so they shouldn't have DNA. Dinosaurs have some DNA, but no full strands of DNA. Is this finding consistent with what Spike said, or should there be no parts of DNA at all after 6 million years?
There should be no parts at all after 6.8 million was the actual number. The half-life of DNA was fairly quick, on the order of hundreds of years, if I remember correctly. That's from memory, that may be wrong. But if you extrapolate that over time, there should be no intact base pairs left after 6.8 million. So yes, we don't have full strands of DNA in dinosaur tissue, but we do have partial pieces of it. But we shouldn't even be seeing partial pieces after 65 million. So yes, thank you, Vince. That was a good question.
Okay. Can you briefly discuss the implications of these 2 laws to information? Mass, energy, how mass and energy and information go together.
Right. Yeah. People have taken the idea of entropy and extrapolated it into information theory and other things. That's very interesting, but number one, it's not really something I feel qualified to talk about. And number 2, having been trained in classical thermodynamics, that's I don't want to say that I don't like using the word entropy in that sense, but I think it can get confusing if we start using a word in ways that it wasn't originally intended. So I like to limit my discussions of entropy to the classical meaning of it and the implications physically. In information theory, I mean, it's a fascinating subject and it's something I'm learning about, but it's more immaterial, and I don't mean immaterial as in irrelevant. I mean, it's non-material, non-physical. And so some of the concepts within it are harder to grasp. I believe it's a valid, you can make valid arguments from it, but it's kind of harder to explain. And, what does it mean when information has grammar and syntax and that kind of thing? And it's harder to come up with day-to-day analogies of where we would see that applied in our daily life. So it's something I'd like to something I'm working more on and not something I feel comfortable talking about yet.
Okay. Well, do you feel comfortable talking about the horizon problem?
The horizon problem is the idea that from a Big Bang perspective, we are, okay. This is actually a relevant question because it is relevant to thermodynamics and heat transfer. So if you have two things that are in thermal contact so they can transfer heat, then given enough time, they will be at the same temperature because heat will equalize between the two. However, if things are not in thermal contact, then they are going to be at different temperatures unless, for some amazing coincidence, they were formed at exactly the same temperature from the very beginning. The Big Bang model says that opposite sides of the universe have never been in thermal contact because there has not been enough time for heat to transfer from that part of the universe all the way over to that part. However, the entire universe is basically the same temperature to within like 1,000th of a degree. So it appears as if the universe has been in thermal contact and is therefore the heat has distributed itself equally, when according to the Big Bang model, even given almost 14 billion years, there hasn't been enough time to do that. This was one of the reasons that the cosmic inflationary model was invented, and I don't want to go through too much of a rabbit trail. But the horizon problem is one of three fatal problems to the Big Bang model, strong predictions that it makes that are falsified by the evidence, that in order to solve them requires something called, this cosmic inflationary idea, which is outside of physics, requires a particle that no one's ever seen and there's no room for within physics, and so on. That probably wasn't a very coherent answer. But the horizon problem is that the different parts of the universe have apparently equalized themselves temperature-wise. They're at the same temperature. But even with 14 billion years in the Big Bang model, there hasn't been enough time to do that. So it's interesting in the origins debate because evolutionists say, well, if the universe is only 6,000 years old, how has there been enough time for starlight to get here from distant objects? There's actually several potential ways that could have happened. And I don't want to derail our discussion tonight with that. My point for now is the horizon problem means that the Big Bangers, quote unquote, have their own version of that problem. They don't have enough time in their model for heat energy to transfer from that part of the universe over to that part of the universe, but it apparently has done so. So they can't point fingers at us and say, you have a distant starlight problem, a light transit time problem, when they have a similar problem of their own. Hopefully that was a useful answer.
That makes sense. And then, okay, we have one more science question from Jeff. He asks, is perpetual motion possible according to the laws of physics?
No, because you can't have a 100% efficient product. Okay, so common example, when you walk, would it be possible to walk if there's no friction between your feet and the ground? Like walk on slippery ice. No, you're going to slip and fall. You need friction in between your feet and the ground. Well, friction is going to produce heat, right? Rub your hands together, you feel warmth, right? Where's the heat coming from? Well, it's coming from the motion that is in what you're doing. So if you rub your hands together, you're burning some small fraction of kilocalorie and converting sugar in your muscles into heat energy between your hands, which then dissipates in the atmosphere and goes out into space eventually. So second law of thermodynamics at work. This is relevant to perpetual motion because of any physical process, there's going to be friction of some kind or some other mechanism by which energy is lost. Perpetual motion means the energy stays in the system forever, but thermodynamics says that that's not going to happen. So a lot of engineering is spent in ways to make things more efficient and reduce energy loss, but you're never going to get the energy loss down to zero. There's always going to be some loss, which means perpetual motion is never going to happen. Whatever machine you start is going to wind down eventually, unless you keep burning fuel and some other way to power it.
That makes sense. Okay, so one more question to leave with is somebody is asking if you could explain briefly your testimony of how you came to Christ.
Oh boy. Well, I mentioned in this presentation, it hinged off of the secular dilemma. I was talking to a Christian coworker while in the space program about origins, and the conversation started by me finding out he was a Christian and a creationist, and me starting to ask him all the questions about how did he deny all this evidence for evolution, and he wanted to know what evidence I was talking about. So I was talking about fossils and radiometric dating and all of this stuff, and he was very, very well versed in creation materials and had answers to all my questions. A lot off the top of his head. Sometimes he had to go look something up first, but he had answers to everything. And I thought it was a very interesting perspective. I didn't necessarily accept his entire worldview, but I at least saw that some of the evidence I thought I had wasn't actually good evidence after all. Then he turned the tables on me and said, I've answered your questions, now you can answer mine. I said, that's fair. He said, you believe in the laws of physics, don't you? And I said, yeah, we use them here every day. And he said, well, how do you reconcile them with the Big Bang model? And thinking about the question, which he didn't even explain, he just let me wrestle with it. That was when I first ran into what I now call the secular dilemma, and I arranged it in the way that I did, realizing that in any form of secular history for the cosmos, you're going to wind up violating physics in your model somewhere along the way. And that was unacceptable to me because I love physics and I want to be consistent with that in my thinking. Hadn't really tried to combine the laws of physics in the Big Bang model before, but now see that these problems exist. And that began almost a year-long journey of investigating all these sorts of questions and basically trying to disprove my friend's Christian worldview. I didn't go down this path wanting to wind up where I have. I went down this path trying to find a way out of it, essentially. And after going through a lot of investigation, every area of science I felt comfortable with digging into, eventually came to the conclusion that it all pointed the wrong way. And now what am I going to do with that? Struggle with that for a while, and then eventually realized that, wait a minute, back up a minute. I didn't want any of this stuff to be true because I understood the implications. If we're created, then there's a creator and we're accountable to the creator. And after other investigation, I concluded that of all the possible creators, the Bible is the only accurate description. I mean, there's all these various religions in the world. They all have problems except for the Bible. The Bible is supportable historically, scientifically, and everything else. So that if we can know anything, then we can know that the Bible is an accurate historical work, et cetera. So I understood that if we're created, there's a creator. I'm accountable to that creator. The Bible tells me who he is, but I don't like that idea because it means I'm accountable for my sin, and struggled with that for a while. By this point, I accepted that creation had to be true, but I didn't want to accept the overall context as well. So in this sense, I became a creationist before I became a Christian. Eventually realized that the gospel message that I had heard 15 years earlier, but rejected because of science, I said, wait a minute, hey, stupid, if creation is true and the Bible is true, that also means the gospel is true. Yes, you're a sinner deserving God's wrath, but God knows your sin better than you do. At the same time, God loves you enough, despite your sin, to have sent his son to pay for it all and reconcile you to himself. And so when that realization finally hit me, I was like, well, wow, this really is the good news. It's like, what better news could there be? So that was the point where I became a Christian. And I usually open my talks with a brief mention that science is not sufficient to make you a Christian. I mean, creation talks are important, certainly, but we're removing stumbling blocks from people in a sense. I became a creationist before I became a Christian because of, the process I just told you about. Science alone is not sufficient to make you a Christian. I mean, there are Muslims who believe in creation, right? Becoming a Christian is the work of the Holy Spirit. But creation is still important nonetheless, because there are many like I used to be, for whom science is their stumbling block. And it's important to address that, or I should say, false interpretations of science are their stumbling block. We're presented as if evolutionary models and secular this and that are valid ways of looking at the evidence when they're not. There's evidence that's not being addressed, and there's evidence that is being addressed but being misinterpreted. So I think it's important to correct misunderstandings, correct misinterpretations, talk about things that aren't normally talked about, because a true view of science confirms creation.
Yeah, and that's That's, but that's a really great encouragement for a lot of the people that are here in attendance tonight, because we study creation apologetics and we study creation science. So, and we do have speakers who talk about the logic side of it, the presuppositional side of it, how it really matters what a person's worldview is, and all the evidence in the world can't convince somebody if they are not going to
Right.
change their worldview. So, but we also study the creation science, and it's good that we get to hear an amazing example of how somebody used that study to show themselves approved unto God. They were ready to give an answer, so
Yes.
they had those things. And so they were able to have that impact on you, and you've used that so much to glorify the Lord, and he's recompensed that. So, thank you again for tonight. And do you want to tell everybody one more time where they can find you? And I mean, we see your slide here on the screen still, creationastronomy.com, but just a little overview one more time about who you are and how people can get in touch with you.
Sure. Well, creationastronomy.com, as you see there, is my site. But the primary thing right now is the email newsletter. I mean, I do offer the videos on the front page. In terms of keeping in touch, there's a way to send me a message at the bottom of every page. I do receive messages. I'm behind in responding often, but that is the way to contact me through the site. The James Webb article that I mentioned a moment ago, if you go to creationastronomy.com/articles, I believe that's plural, articles. There's a list of all the articles that I published there. The very top one is on the James Webb. It's a long article, but worth reading if you're interested in this kind of stuff, because there's lots of good stuff coming out of that.
Yeah, for sure. Okay, so, and of course, we're Creation Fellowship Santee. We're happy to have a lot of people new with us this week because of your talk. So that's been a blessing, and people can find most of our past presentations by typing in tinyurl.com/C like creation, F like fellowship, and S and the word Santee, which is spelled SANTEE. Or you can email us at creationfellowshipsantee@gmail.com to get on our mailing list. Next week, we have Dr. Jason Lyle. He will actually be here to talk about physics. So specifically, he did a series on quantum particles, and he'll be discussing that with us. So with that, we're going to go ahead and end our live stream.